For the rest of this unit, we're going to take a closer look at the solar system bodies individually. We're going to start with the Earth and the Moon. Even though we think of Earth as being rather separate from space, it's important to understand how processes that occur on Earth can tell us about how similar processes occur on other planets. Just to review, remember, the nebular theory is the idea that all the objects in the solar system formed from the same nebula, a cloud of gas and dust in space. This cloud was made mostly of hydrogen and helium, the two simplest elements on the periodic table. Here you see a nice image of a nebula. That nebula then begins to be pulled together by gravity. The sun begins to form in the center, and the small protoplanets and planetesimals form as material farther away from the sun begins to clump up as well. These two words, protoplanet and planetesimal, are used interchangeably. They just refer to the small baby planets that will combine over time to make larger planets. Proto-Earth, or baby Earth, was actually larger than it is today. It was of homogeneous composition, meaning that it didn't yet have a crust, a mantle, and a core. It was the same all the way throughout. The prefix homo means same. It would have been a very unpleasant place, with meteorites crashing down on it all the time, as more and more material built up these early protoplanets. At one point, a Mars-sized object collided with the Earth. This collision actually created the Moon, but we'll talk more about that later. Early Earth was hot, not just because of all the objects colliding with it, but also due to radioactive heating. As radioactive atoms break down into smaller atoms, they release heat. Additional heat is generated as gravity crushes the planet down. All of this heat causes the planet to begin melting, which leads to the process of differentiation we talked about in the last lecture. Make sure you understand the processes of accretion and differentiation. To understand differentiation, you need to know how density works. Something that has high density means it's very heavy for its size. For example, a brick is a lot heavier than a brick-sized box of Kleenex. Brick is much denser than Kleenex. The denser materials in the semi-melted Earth begin to sink and form Earth's core, while the lighter materials float to the top and form the mantle and crust. From the amounts of radioactive materials that have broken down over time, we can use mathematics to calculate the age of the Earth. Different radioactive materials have different half-lives, which is the amount of time it takes for half of the radioactive material to break down. Looking at these remaining amounts, we can tell that the Earth and the rest of the solar system is about 4.6 billion years old. Here's how it works. Take a look at the image. Imagine that 4.2 billion years ago, there was a sample of uranium-235 that contained 1 million atoms. The half-life of U-235 is 700 million years. So 3.5 billion years ago, or 700 million years later, only half of the original uranium atoms remained. The rest had been converted to lead-207. Another 700 million years later, or 2.8 billion years ago, that number was halved again. This process continues until no atoms of the original sample remain. Notice that today, some of this original uranium still exists. You may then wonder why, if half of it breaks down in the first half-life, why doesn't the second half of it break down in the same amount of time, leaving nothing left? It all comes down to collisions. Particles crashing into other particles is what causes the large atoms to break into smaller ones. Since there are fewer atoms of that type around, they don't crash as often, so the reaction happens more slowly over time. So after the process of differentiation, Earth became a layered structure. Each layer is characterized by different physical properties and different chemical composition. For example, the inner core is made predominantly of solid metal, while the mantle is composed predominantly of silicate, rocky materials that can flow. You may wonder how we know that the Earth is layered, since we can't actually drill down through thousands of kilometers of rock to see what's down there. We can actually use earthquakes to determine this. Different types of earthquake waves can penetrate through different types of materials and travel at different speeds. For example, P waves can travel through both solids and liquids, but S waves can only travel through solids. When an earthquake happens, seismometers, or earthquake measuring equipment, picks up these different types of waves all around the Earth. Which types of waves are detected at different seismometers can actually give scientists a very good idea about what different layers of the Earth are made of and whether those materials are solids or liquids. NASA's InSight lander on Mars will hopefully be able to give us similar information about Mars in the near future. As I mentioned, the crust and mantle are made mostly of rocky silicate materials. The crust materials have lower density than the mantle materials. The core is mainly metal. The outer core is so hot that it's a liquid, and the inner core is even hotter, but it's actually compressed back into a solid because of the huge amount of pressure from the material on top of it. As Earth spins, this liquid part of the outer core also rotates. This generates a magnetic field that surrounds Earth. This magnetic field is really important to life on Earth, as the magnetic field protects us from harmful radiation from the sun. Not all planets have this protective field. The crust and hard outer part of the mantle creates Earth's hard shell called the lithosphere. Its thickness varies by location. The crust is thinnest under the oceans and thickest under high mountains. Earth's tectonic plates are made of chunks of lithosphere that float on the mantle. The crust in different areas also has different chemical composition, meaning that it's made of different types of rock. Oceanic crust is made of denser rock, while the crust that makes up the continents is less dense. Here you can see again how much thicker the continental crust can be. As the partially melted Earth was differentiating, gases were released from the molten interior that formed our atmosphere. Most of the early atmosphere was water vapor and carbon dioxide. There would have been hydrogen gas as well, but those atoms are so light and move so quickly that they were actually lost to space. Notice there is no oxygen on this list. The atmosphere has changed a lot over time due to both geological and biological processes. Photosynthesis, for one, has changed much of the carbon dioxide that was in our early atmosphere to oxygen. As Earth cooled, this water vapor in the atmosphere was able to condense and fall back to Earth's surface as rain. The oceans have probably been around for 4 billion of Earth's 4.6 billion year history. Some of Earth's rocks were soluble, meaning that they could dissolve, and these dissolved rocks contributed salt to our oceans. Much of this dissolving was due to very acidic conditions on early Earth. This image shows the process at work. As gases were released from the Earth, especially from volcanic vents, the water vapor collected in the atmosphere. Clouds formed as the vapor condensed onto dust particles into the air. Then the rain was able to fall back to Earth. Here is a cross-sectional view of the upper part of Earth. Plate tectonics is the theory that describes how Earth's tectonic plates move relative to each other. We can see different tectonic plates and what happens over time as they move. Notice the subducting plate forming a trench, mantle material rising up at a volcanic island, the underwater mountain range, and the coastal volcanoes. Let's look at each of these individually and how they happen on Earth. We'll compare those features to those we see on other planets to try to understand what's happening in those locations. 3 different things can happen where plates meet. They can come together, separate, or slide past one another. Divergent boundaries occur where plates move apart. Here, we see a chain of underwater volcanoes where 2 plates pull apart and magma reaches the surface, creating new rocks. You can model this by simply pulling your hands apart. Convergent boundaries are where 2 plates come together. Here you can see that as one plate gets pushed under another one, we call this subduction, the crust gets crunched up, creating a chain of volcanoes. You can model this by bringing your hands together and forcing one hand below the other one. Transform boundaries occur when two plates slide side by side. Earthquakes often occur at this type of boundary. You can see a fault line here has split the volcanic ridge. You can also see an island here formed at a volcanic hotspot. Sometimes chains of islands form from a single hotspot as the tectonic plate moves. The Hawaiian Islands were formed in this way. Here is a map of Earth's major tectonic plates. Notice each continent is primarily on one plate, but sometimes it is split. Notice this bit of Mexico and California that is not on the North American plate. This is why they have so many earthquakes on the west coast. Those plates shift back and forth there. Also notice that India is not on the same plate as the rest of Asia. These plates are converging. That's why huge Himalayan mountain range exists. Here's another map of the location of Earth's volcanoes and earthquakes. Flip back and forth between this image and the last one. Notice how almost all of the volcanoes and earthquakes happen along plate boundaries. Earth's continents have been moving for a long time. The theory of continental drift was proposed over 100 years ago by Alfred Wegener. He realized that locations that are now far from one another share similarly shaped coastlines and have the same types of fossils and mineral deposits. He realized that millions of years ago, Earth's continents were once joined together in a single landmass he called Pangaea. This shows some of the fossil evidence supporting Wegener's theory. Today, different animals exist on different continents. For example, Africa has lions, while North America has wolves. But millions of years ago, the continents that are now far apart had the exact same plants and animals, suggesting that back then, the land masses must have been connected. People didn't believe Wegener at the time, though, because he could not explain how these huge continents could have moved. But now we can explain it. The theory of seafloor spreading shows us how continents separated back then and how they still move today. New crust material is made at the mid-ocean ridges. Lava erupts up, hits cold ocean water, and forms rock. This new rock pushes old rock out to the sides, separating the land even more. But Earth isn't getting bigger, even though new crust is expanding at mid-ocean ridges. It's shrinking in other places called trenches, where one plate subducts under another, getting remelted in the mantle so that it can erupt again later at a mid-ocean ridge. It's rock recycling. We can prove this seafloor spreading has occurred for thousands of years by looking at the magnetic field stripes on the ocean floor. You can't see them with your eyes, but these stripes can be measured with special equipment. Compasses point north. Imagine this dark orange stripe as newly created sea floor. If you took your compass down there, it would still point north. But if you moved farther from the ridge into the white area, it would point south. Moving farther away into the lighter orange stripe, the compass would point north again. The ocean floor shows us matching patterns on each side of the ridge, proving that these rocks are the same age as one another, just spread out over time. We still don't understand fully how and why the Earth's magnetic field flips direction, since it hasn't happened since we've had technology to measure it, but we're actually overdue for a change. Here we see another image of subduction, one plate being pushed under another one. The area where this happens is called a subduction zone, and this is one type of convergent boundary. The oceanic plate is denser and dives below the plate carrying the continent. See the volcanoes here? As the oceanic plate subducts under the continent, the crust above it gets pushed up, forming folded mountains. The deeper the subducting plate goes, the hotter it gets. The rock melts into magma. Melting makes it less dense, and the magma begins to rise. Pressure builds up, and eventually it will erupt as lava onto the surface. Another type of convergent boundary can happen between two continental plates. As India smashes into the rest of Asia, There's nowhere for the land to go but up. Mount Everest, Earth's highest mountain, is actually still growing as the plates continue to push together, forming the Himalayan mountain range. Divergent plate boundaries often occur in the middle of the ocean at mid-ocean ridges, but they can occur on land too. Have you ever noticed the chain of lakes in eastern Africa? The African continent is literally being ripped apart. As the plate separates, blocks of crust subside or fall down into the gap. Water fills in these low areas, creating lakes. In millions of years, the Horn of Africa here will no longer be attached to the rest of the continent. Here is another image of the transform boundary at the San Andreas Fault. You may have heard people say that California is going to fall off into the ocean. That is completely false. It's not going into the ocean, but it is moving north. So maybe one day, Los Angeles will be far enough north to be a suburb of San Francisco. Those are the general things you need to know about Earth. Now let's take a look at the Moon, our closest neighbor in space. The Moon is Earth's natural satellite. We often think about satellites as being man-made craft that bring us cell phone service, but satellite is just really one thing that orbits around something else. There are over 200 moons in our solar system, but Earth has only one moon. Our moon lies about 250,000 miles from Earth. Its diameter is only about 1/4 that of Earth's, and it has only 1/81st of its mass. This means that the moon is mostly crustal and mantle material with very little dense core material. This led to the idea that the moon was actually born from Earth. Models show that a Mars-sized object impacting the Earth would have left most of the core material behind with the Earth, but a large amount of lower density crust and mantle material would have been ejected into space. This material would have formed a ring around the Earth that would eventually coalesce together, forming the moon. Here is an artist's conception of how this might have occurred. You see the impact and the ring material. Accretion is the process where that ring material would eventually clump together, forming the moon. Looking at the moon, you can see that it is heavily cratered. A period of time about 3.8 billion years ago, called the Late Heavy Bombardment, saw both Earth and the moon getting impacted by lots of objects. Some of these impactors were very large. They could actually punch through the young moon's crust, forming lava lakes. These lakes eventually cooled, forming darker, smoother areas on the moon called maria. Maria is Latin for seas, and although they aren't water seas, people once thought that these areas of the moon were water. There are many of these seas on the near side of the moon facing the Earth, and almost none on the far side of the moon, which you will see momentarily. The moon is a differentiated body with a crust, a mantle, and a small core. We don't know whether any of the moon's interior is still molten. We don't see any active geologic features on the moon, but we have measured moonquakes. The moon has no atmosphere. There is no liquid water, and there are very extreme temperature differences between the sunlit side and the dark side of the moon. Though the Earth sits about the same distance from the sun as the moon, the Earth doesn't have these wild temperature fluctuations. Yeah, it's colder at night, but maybe 20 degrees, not 300. Earth's atmosphere regulates Earth's temperature, but since the moon has no atmosphere, the temperature changes wildly. As the moon is much smaller than the Earth, it has much less gravity. The moon's 1/6 gravity is why you see lunar landing astronauts almost bouncing as they walk. We're now going to go through 3 important types of surface features on the moon. The first is called the lunar highlands, which are mountain ranges on the moon. You see some of those mountains here. We think these crack-like features formed as the moon cooled over time. in much the same way ice cracks when you drop it in a glass of water. The second important landform type on the moon are the smooth, darker areas called maria. They are smoother than the rest of the moon because they cooled after most of the crater-forming impact events occurred, but you can still see some craters within the maria as well. Here is a graphic showing how we think the maria formed. Impacts would have shattered the rock into which they occurred, and the magma would well up from below, filling the crater with lava that would smooth out and form a new surface. The maria appeared darker than the mountainous regions of the moon because they formed from this mantle material that is a different type of rock than the crust. This radar image shows you the smooth maria on the near side of the moon that look very different than the rough, heavily cratered surface on the far side of the moon. Craters are very common on the moon, and they can be up to 2,500 kilometers across. These are predominantly structures formed from meteorite impacts, but some could have been formed in volcanic events. Larger craters often have little areas of mountainous uplift in the center. Here, you can see a crater-forming event. As the object collides with the moon, the material is thrown up into space, excavating a deep hole. Sometimes a small rebound structure occurs in the center, making a peak where the object actually hit. Craters can tell us the age of the surface. Areas that are more heavily cratered must be very old. Areas with fewer craters, like the maria, must have formed more recently. In the first image, we see a string of craters that formed when an object was torn apart gravitationally before it impacted, creating a chain of craters. This chain of craters is not on our moon, but one of Jupiter's moons called Ganymede. This surface is much older than the one in the image on the right that has many fewer craters. Sometimes crater ejecta, material that's thrown from a crater, makes rays on the surface. Can you see them here? This crater shows the rays really well. Lines of material coming out from the crater are actually material that was thrown out from the crater. Can you see any shapes in the maria? I see Wilma Flintstone. The far side of the moon, as previously mentioned, looks very different from the side closest to Earth. It's much more heavily cratered and has no large areas of smooth terrain like the maria on the front. We can only see this side of the moon when we fly spacecraft around the moon, as the moon is tidally locked to Earth, meaning that the same side of the moon is always facing Earth. The difference between the two sides of the moon is displayed nicely in these two images from the Lunar Reconnaissance Orbiter. Look at how differently the near and far sides of the moon look. The near side has these lower elevation maria, while the far side has much higher, much more heavily cratered highlands, and one really large impact structure toward the South Pole. We think the reason for this is that the moon is not perfectly round. It's more egg-shaped, and the skinnier end of the egg is what points away from the Earth. It has thicker crust, so impactors were unable to punch through the whole crust to form the lava lakes that become the maria we see on the front side of the moon. Here's the same pair of images showing elevation differences. Lots of lower elevation maria on the front, one large impact structure, and lots of craters on the back. And finally, here's just an overview picture of the moon with several features labeled. You won't need to memorize the names of specific seas or craters on the moon, but you should be familiar with the different sorts of landforms that occur on the moon, where they are found, and how they formed.